Here you go. Okay, so today we are going to discuss a particular type of functions called recursive functions. Sometimes this programming technique is also called recursion. Okay, so the essential principles are, I would say, derived from induction. So the idea is that if you can solve a problem for small instances and if you can express an instance of the problem in terms of smaller instances, then essentially it says you can solve the problem on all instances. This is basically nothing but induction, right? So you can solve a problem for small instances essentially is the induction basis. Okay, whereas you can express an instance in terms of smaller instances. That means if you can solve smaller instances, you can somehow tie them up together to solve a bigger instance. So that is basically the induction hypothesis. And the conclusion is that you can solve the problem on all instances. So here goes a set of examples. For example, I may do something like this, factorial n. Okay, this can be expressed as n times factorial n minus 1. So this is basically the inductive step. On the other hand, if you start with something like factorial 0 equal to 1, this is what is meant by this for small instances, then you can compute factorial n for all n. Okay. Similarly, we have already seen GCD of AB can be expressed as GCD of A%B. Sorry, made a mistake. No, this is fine, but anyway, I will write it later. Yes, GCD of B and A% B. Okay, of course, here I assume that A is greater than equal to B. And so this is essentially expressing this to the same problem, but with smaller arguments. Okay, and you may actually consider this as the smallest possible instances. When the second component reduces to 0, then you know, so the GCD of A and 0 is A. Okay. And maybe I give you a third example to illustrate my point. You might have heard about the so-called Fibonacci numbers. So F0 is defined as 0, F1 is defined as 1, whereas for n greater than equal to 2, the nth Fibonacci number is the sum of the previous two Fibonacci numbers for n greater than equal to 2. So these are my small instances, whereas this last equation is expressing the nth Fibonacci number in terms of Fibonacci numbers of smaller indices. Okay. So this kind of mathematical formulation or procedural formulation, which essentially relies upon induction, is at the basis of recursive functions. Okay. So I start with a couple of examples. GCD thing we have already seen, so I will concentrate on this factorial and Fibonacci numbers. So let me write a code for it. Factorial, let's say int n, or assume that this is positive, non-negative at least. If you want to ensure that, just call it unsigned int n. Anyway, so you work with the hope that n is positive or non-negative, more precisely. Then if n is equal to 0, then return 1, whereas in other cases return n times factorial n minus 1. So this is nothing but converting this definition of factorial to the C format. Okay. So why this factorial is called a recursive function is that this is the name of the function, and inside the function body it calls itself. Okay. So this is a function that calls or invokes itself. But of course, in order that this sequence of calls does not lead to an infinite sequence of calls, there is a necessity that there happens something in the argument. For example, here this argument decreases by 1. Therefore, this call cannot continue infinitely. Okay. So such functions are called recursive functions. And let me also translate this recursive definition of Fibonacci numbers to a so-called recursive function. This is fairly straightforward. Int Fibonacci, or maybe I just call n. So if n is 0, again I assume that n is positive or non-negative. If n is 0, return 0. If n is 1, return 1. Otherwise, under the assumption that n is positive, n is greater than or equal to 2, so you just return f n minus 1 plus f n minus 2.
Sir, if n equal to 0, it should return 1, right? 1, 1, 2, 3.
First term is 0.
F0 is 0, F1 is 1.
Okay.
Okay, so the sequence starts from 0 in this fashion. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay, and so on. 55, blah, blah, blah. So this is the 0th one. This is the first one. This is the second one. So that is the convention. Okay. Okay.
Okay, so go ahead.
Excuse me, sir.
Yeah.
So in Fibonacci, we take a sum of previous two terms. If we
Yeah.
take three terms, then this is also some special sequence.
I do not think it has any special name, but of course we can have.
Yes, it is known as Fibonacci sequence.
What sequence?
Yeah, it's a just special name. So it's known as Fibonacci sequence.
Fibonacci. Okay, maybe people have given some
It's
names.
just a special name given by mathematicians.
Okay, maybe something like that. But anyway, the idea
That
is,
also lead to some constant.
yeah, of course. You can have a variety of such so-called linear recurrence relations. And there is a way to solve such recurrence relations, but you don't need to worry about this because this is well beyond the scope of this course. I'm just demonstrating how I can translate a recursive mathematical definition into the language that a C program can handle. Okay, so this is just a direct translation of this. Okay, if n is 0, these are basically the base cases. And this is basically recursion, or you may call induction. Okay, so recursion, or if you want to view it in inductive way, this is induction. Okay. Once again, this function f is called recursive because it's called f and it makes two calls of itself. But in order that this recursion eventually stops, the arguments are smaller, n-1 and n-2.
So n is term now.
N is?
User will consider n as term. Fifth
Term means,
Fibonacci sequence, right?
term means if you have a
Fifth
sequence.
sequence. What
Okay.
is the fifth Fibonacci number?
Yeah. If you have a sequence, I can also, of course, consider it as a function. This is a of 0, this is a of 1, this is a of 2. Okay. So sequences often in mathematics start with the 0th star. Okay. So if A is capital F, this is the 0th Fibonacci number. If this is F1, this is the 1th Fibonacci number, and so on. Okay. So if the user enters n, and if you call f of n, then it will return the nth Fibonacci number, of course, under the assumption that the number is positive or non-negative, to be more precise. Okay. So let us see how this particular function, particular call, develops into a tree of function calls. Okay, so this is often called the recursion tree. So let us take maybe a smaller thing, not a very large thing, n equal to 5. So if I call f5, it in turn calls f4 and f3, and then definitely it adds up the two values to return values and returns to the caller. Likewise, f3 calls, sorry, f4 calls f3 and 2, this calls f2 and f1. F3 calls F2 and F1. This F2 calls F1 and F0. This F2 calls F1 and F0. But note that whenever I have reduced to the case n equal to 1 or 0, this, okay, let us see. First, let me complete this tree. That's 0. Okay. Now you recall that when n reduces to 0 or 1, then we are making no further recursive calls. Instead, we are just returning n equal to 0. If n equal to 0, it is 0, or if it is 1, it is returning 1. So this guy, f1, this will return 1. And this guy, this will return 0. So it is the task of this invocation to add these two up, 1 plus 0, and return that thing to its parent. 1. This one, 1. This one returns 1. This one returns 0. This returns 1. This returns 0. This function, this invocation adds these two return values up, 1 plus 1, 2, and returns that to the caller. What happens to this 1 plus 0? So this computes 1 plus 0 and returns the value 1 to the caller. Here it is 1 plus 0, it returns 1 to the caller, and this is no recursive thing. It will simply return 1. Okay. Then let us see which one I have not yet considered, F4. So this gets 2 from the first recursive call, 1 from the second recursive call, then this adds them up and sends 3. Okay, to the caller. Here 1 plus 1 added by this invocation, 2. Eventually F5 gets 3 and 2 from the 2 recursive calls. It returns 5, maybe 2 main. Where you called. So let us see that this is 5. 0, 1, 2, 3, 4, 5. So the fifth one is 5. Agree? Are you convinced how this kind of recursive functions work? There are a lot of other issues I need to talk about, but first let us understand that you really got a understanding how recursion works. Any questions on this? We will do much more complicated things than just computing Fibonacci numbers using recursion. But at least this initial things you should understand. Otherwise you will get stuck. So yeah, so if there are any questions, please let me know.
Sir, for each term, it will be calculating by recursion tree.
No. Recursion tree is essentially, I would say, a what would I say? It's a pictorial description of how different invocations of F are interrelated. In the topmost call, which is made from main, you are calling F with an argument of 5. Now this 5 is not 5 equal to 0, this is false, 5 equal to 1, this is false. So this invocation of F5 will make two recursive calls, F4 and F3. So this first recursive call is with argument 4. The second one is on argument 3. So this is what this F is called from main. It makes two recursive invocations, two calls, one on index 4, one on argument 4, the second one on argument 3. And this one, this itself, this is 4 is not 0 or 1, so it makes two further recursive calls. This makes two further recursive calls. So this is basically a pictorial description of the entire computation done by the recursive function. Okay, so this is just for your understanding.
That is, recursive function works in this way. That is, it calculates by recursion tree value.
Conceptually, yes, but I will tell you later how a computer actually handles this. Of course, it does not expand the entire tree, and one important thing is that when you call this F, this invocation is running only. Okay, the other tree has no existence. Then when this is running, you make a recursive call of F4. Okay. Now, when this F4 is called, until, or I would say until this function returns a value, the function f5 is not going to make second recursive call. Let us look at this. Of course, the C is not fully specifying things this way, whether this is evaluated first or this is evaluated first, but let us make an assumption that from left to right this is evaluated. So f5 first makes a recursive call. Okay, so these are not two parallel calls, right? After this function returns, some value is stored, and then the second recursive call is made. And when that call also returns, these two values are added up and eventually returned by this. Okay. So we will soon see, if not today, in the next class, that the computer manages it, the compiler manages it using what is called a recursion stack. We will see. Okay. And this is, so the computer first calls this makes a recursive call this, then 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 this call returns, so then this makes a recursive call, then this function returns, then adds up, it goes there, makes the second call, which immediately returns, then this, then this, then this, then this, then this, returns, and this calls these, and this calls this, and this calls this. When this returns, this second call is made, and this. Okay, this way it goes. In fact, in technical terms, this is called a binary tree, and the kind of traversal is called a post-order traversal. But you don't need to worry about all these sophisticated terms. This is the total computation done by the recursive function, but at any point of time, there is exactly one recursive call is active. Okay. For example, when this makes this call, this is active. After this returns, this becomes once again active and makes the second recursive call. And when this returns, it adds up, and this f5 is waiting for the value of f4. So when this has computed the value 3, it passes to that invocation. Now this again becomes active, makes the second recursive call. This way it happens. Okay, and we will see how we can manage this using a so-called recursion stack or call stack.
Sir?
Yeah.
Sir, compared to a for loop, won't this recursive function take a lot of computational power?
Yes. Yes, obviously. In fact, this is exponentially poorer than I would say, an iterative thing. But I have taken this example in order to illustrate how recursion works. I will give you more meaningful examples in due course of time. Okay, but this is just for explaining to you how recursion works. You tell. Okay. So, what next? There are lots of things. Okay, so let us look at one particular point of time. Maybe F4 has called, sorry, I start with F5. F5 called F4. F4 called F3, and let's say that F3 returned. F2, then it recursively calls F2, and then it calls F1. Okay. So what happens is that when this call is made, this is the active call. This is waiting for this. Yeah.
Sir, you skipped F3, sir?
No, I didn't skip. I assume that F4 makes the first call F3, that is returned, and then makes the second call F2. Okay, I deliberately didn't use F3 here. Okay, if it is factorial thing, then I have to list everything. Right, F4, you look at this picture. F4 is make two recursive calls, F3 and F2. I assume that this has returned, So I am essentially in this path. When I am talking about this picture, I am essentially talking this path in the tree. F5, F4, F2, F1. Okay. Okay. You can see it, right? F5, F4, F2, F1. At one point of time, this is configuration. F5, F4, F2, F1. Okay, so this guy is just going to return 1, and this is just waiting for it, and this is just waiting for it. This is just waiting for this. And after this wait is over, they will possibly make a second recursive call, or they will just add the 2 return values and return to this. So this is done in main. So main is basically waiting for this value F5 to return some value to it. Okay, this is how it works. So the thing that I want to mention is that there are now 4 instances of Fibonacci running. Okay, so what are the scopes? Okay, so you look at this. If I slightly change this function this way, instead of just doing this, I will just use a local variable s, and instead of immediately returning this sum, I will just store the sum in this, and then I will say return s. So this is of course not needed, but this is what this is introduced in order to explain the scopes. So this sum variable s is inside the invocation, is inside the scope of every invocation. Okay, this has some s, this has some s, this has some s, and this has some s. Okay, the point is that these 4 invocations which are active or waiting at any point of time, at this point of time, I would say, each has a local variable s. And you must understand that whenever this refers to s, this refers to the local variable of this invocation. And whenever this refers to s, this essentially refers to the local variable, okay, s corresponding to this invocation. Okay, in other words, these 4 instances, they have mutually exclusive scopes. So nothing essentially is shared. Okay, but there are certain things that can be shared, but let's not worry too much about that. They are mutually exclusive. So the local variables of this invocation and the local variables of this invocation, they are completely separate. Okay, so they are not shared. Okay, so if this invocation has its own set of local variables which have nothing to do with the local variables of the caller function. Likewise, these local variables have nothing to do with this. Okay. So each individual invocation has its private local variables. Okay. So some variables are shared. These are called static variables. Let's not worry too much about it. So maybe if you are interested, you can just look at other things like C books or even the slides that we have already uploaded. So let's not worry too much about the static variables. So local variables which are not static, they are mutually exclusive. Whenever I refer to S, in this invocation, it's the S of this. When I refer to S, it is S of this, and so on. Okay, is this idea clear? So that if you make any change to the value of S here, okay, that in no way is reflected in the value in the variable that is called S in this invocation, and conversely. They are completely separate things. Okay.
Yes, sir.
Oh, good. So with this understanding, let us proceed. What next? Okay, maybe. There are lots of things. I think I need another hour. Maybe that recursion stack thing I will take up later. Let me give you a more complicated example like this. Okay, so first let me recursively formulate the problem, and then I will write a code to demonstrate how it works. Printing all permutations of, let's say, 1, 2, 3 up to n for a positive integer n. Okay. So I will write a recursive function which illustrates quite a lot of things, but it is very difficult to understand. What I will do, first I have to make a recursive formulation. Maybe once again, let us restrict to the special case n equal to 5. So I will start by writing 1, 2, 3, 4, 5 in an array of size 5. Okay. So if I call this array A, then A0 gets, sorry, AI gets the value I plus 1 for I equal to 0 through n minus 1. Okay. So I start with this permutation. Then what I will do, one by one. Okay, so
Sir, 1 second. Can you explain the question meaning, like printing permutations of 1, 2, 3 to n?
I will essentially print, so n is 3.
Different arrangements?
Yeah, permutation means arrangement.
Oh, acha. Got it.
So I will essentially print this 3, 1, 2 and 3, 2, 1. Okay.
Got it, sir. Got it.
Okay, fine. Okay, maybe arrangements, permutations is also quite, I would say, a standard term. Anyway, so you see that some of the permutations will start with 1, some of these permutations will start with 2, some will start with 3. Now, if I look at the remaining part, when it starts with 1, so this is the set of all possible permutations of the remaining numbers, or arrangements. If you want to call it arrangement, this is fine. Similarly, if I put 2 in the first position, then this is the set of all permutations generated by the remaining numbers. And similarly, if the first thing is 3, then this is the remaining thing. I will recursively generate all possible permutations of the remaining numbers. Okay. And of course, here the problem is about 1, 2, 3, 4, 5. But if I look at this, this is 2, 3. This is not 1, 2. This is 3, 1 or 1, 3. This is 1, 2. Okay. So what I will do one by one, Of course, I have 1 here. But anyway, if I put 1 here, and I can recursively generate all possible permutations of this, then essentially this list is done. Then what I will do, I will swap 1 and 2. And recursively generate all possible permutations of this. Then I will once again move it back to this 1, 2, 3, 4, 5, and then I will swap 1 and 3. Okay, and bring this 3 here. That means I will have 2, 1, 4, 5. And then I will recursively generate all possible permutations of the remaining 4 elements. And this is, I'll keep on doing until I have considered the last one, which in this example is 5. So 1 and 5, I will swap. I will keep the remaining things as it is, 2, 3, 5, 4, 4, 1, and then I will make a recursive, I would say recursive arrangement or permutation of the remaining 4 elements. Now, if I look at what happens when I look at this case of 4, okay, maybe I just so a call on this will essentially make 5 recursive calls. 1 here with 1 at the beginning position, with 2 at the beginning position, with 3 at the beginning position, with 4 and 5. So it will make 5 recursive calls. Okay. Each recursive call is an instruction to permute the remaining 4 values, 2, 3, 4, 5, or 1, 3, 4, 5, or 2, 1, 4, 5, or 2, 3, 4, 1. Okay. So these are no longer exactly 1, 2, 3, 4. So I in general have a situation like this: Ci plus 1. In this case, of course, it will always be n minus 1. Okay, so this is not exactly 1, 2, 3, 4 or something like that. This may be some other things. So this will essentially make, okay, first it will put Ci in this position. Okay, and recursively it will ask to generate all possible permutations of the remaining elements. Then next one is it will swap with Ci plus 1 so that it's something like this. Then it will ask to make all recursive permutations of this, and so on. The last thing is I will swap Ci with Cn minus 1. Here I will have Ci plus 1, Ci plus 2. But here I have Ci, and I will recursively generate all possible permutations of this. Okay. And when does this recursive calls stop? It essentially stops when I have reached a situation like this. I want to permute. So you see, the outermost call, this is a request to swap, I would say to compute all permutations of five elements. This in turn makes recursive calls, 5 recursive calls to swap, or I would say permute 4 elements. Next level of recursive calls, 3 elements, 2 elements. Finally, and eventually, I will end up with a situation when I am asking to swap exactly 1 element. But 1 factorial is 1, and there is actually I would say nothing much to do, except that I will now print this entire thing. Okay, and 1 element subarray has exactly 1 permutation, so there is exactly a unique possibility which is already stored in the array, and I will now print it and just return. Okay, so this is the basic idea. So I will write a code. I understand that you will have at least initially, quite some problem in understanding how it works, but think about it offline.
Sir, it's only way to do that question, recursion.
I don't understand your query. A problem may be solved in hundreds or maybe even infinite number of ways. This is just one way of doing it. Okay. So maybe int A, of course, I will not use permutations of too many things, so it may be sufficient 10. Okay, I. And of course, I have to have n.
So I have one doubt, like every iterative function, like whatever in whichever program that we can do using loops, can they all be done using recursive functions?
And conversely. Yeah.
Yes, I didn't hear you.
Yeah. Loop you can write in terms of recursion, and recursion you can also, if you use something called a stack, then you can avoid all recursions. Anyway, let's not worry too much about this for the moment. Okay, so the user specifies an end, and then for I equal to 0, I less than m plus I set ai equal to, look at this, initialization ai is I plus 1. Okay, of course, if I wanted to permute 0 through n minus 1, that is also fine, but anyway, doesn't matter. I plus 1. Okay. Then I will make the recursive call permute A. Its total size is n. And initially, I am starting from index 0. Okay. In general, I am starting at index I. So this I have to specify. Okay. Up to what point it is done. Okay, sorry. Initially, I is 0. Okay. Then I write this permute function. Okay, it will just possibly print something. So it is not for the moment needed to return anything. So it's an int array, size is n, and the beginning index, that is I. Okay. And I will have two things, j and t. J will actually imply with which element I will swap the ith element. Okay. And t is a temporary variable that I use for making this swap work. Okay. Swapping can be done without extra variables, but anyway, we will do the standard thing. T equal to I equal to j, j equal to t. Okay. Int jt, int jt, int jt. Okay. So first, let us see if I have reached this position, this one. Okay. When I have reached I equal to n minus 1, then there is nothing to be done. Okay. So if I is n minus 1, then there is no further recursive calls. And what I will do for j equal to 0, j less than n plus j, printf % space a j. Sorry, printf, the new line character, and simply return. Okay, so this is void, so I just say return. Return not any value. Okay. Otherwise, for j equal to I, j less than n plus plus j. I will just swap ai with aj. Of course, if j equal to I, the swapping is not necessary, but anyway, if you do it, it's not a harm. T equal to ai equal to aj, aj equal to t. Then make the recursive call permute a, n is n, sorry, comma, but now you are done with placing something in the ith position. So next recursive call is on I plus 1. And when this returns, okay, again you swap ai and aj so that the array is back to the normal position. Okay. And once again, I am not supposed to return anything, so I do not have to write an explicit return statement after this for loop. Okay, so that's it. It looks like a small code, but there is a lot to understand how this works. Okay. Maybe I give 3. 1, 2, 3, 1, 3, 2, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, and 3, 3, 1, 2. This is precisely what we wanted to do. Okay. If I say something larger, like 4, okay, so it has done this 1, 2, 3, 4, 1, 2, 4, 3, 1, 2, 4, 1, 3, 4, 2, and so on. Okay. And of course, you can specify larger values, 6. Okay, so it's a list of 120 lines. Okay, anyway.
So 720.
6 is 720. Yes, it's a huge thing anyway. Okay. Factorial 5 is 120. Yeah. 720 such values. Of course, I can give even larger things like 10. It will keep on printing for long. Seven in first position, 8, 9, 10, done. Okay. Okay. Now, okay, let me do one thing. Alongside, okay, so is there any query? There must be.
Sir,
Yeah.
sir, this code will not work if the one or more elements of the array are means identical.
Well, so that way permutation is permutation with repeated elements. Yeah, that thing you have to do something else. Yeah.
Sir, don't we have, in that case, don't we have to like specify the array? Since like you're inputting one number means like it would continue from 1 to the end of the number. For example, like 6, so the array is given 1, 2, 3, 4, 5, 6. But if like you want similar elements, then you have to input the array by yourself.
Okay, whatever. You think about modifications for this case, but let me first know that this particular program, the working of this particular program is clear to you. Yes or no?
So can you once explain what we are doing with the swapping? Just we are changing the positions. Like we are first printing 1 in the first place and then 2 like that, right?
No, let us again look at this. The complete recursion tree on, that's a small thing, let's say. So n equal to 3, let's say. Okay. So the outermost call gets this array A as 1, 2, 3. Now what it does, it makes 3 recursive calls. So I is 0 here. So it swaps 1 with 1 or 1 with 2 or 1 with 3. Okay. So it is either 1, 2, 3, or if it is swapped with 2, this is 2, 1, 3, or it is 3 comes here, 3, 1 goes here, and here I have 2. So this makes 3 recursive calls with the array. I would say array changed like this, and once again when it comes back, it will once again make a reverse swap and restore the original array. But anyway, that's not very important. Now here, 1 is sitting at position 0. I am not going to change it. Here, 2 is sitting at position 0. I am not going to change it further because I have become.
Hello, excuse me, sir.
Yeah.
Hello, sir. Am I audible?
Yeah. Tell.
Sir, I am feeling unwell. Can I leave the meeting?
Oh, okay. If you have problems, then yeah.
I am having a heavy fever, sir.
Oh, I see. Take care.
Thank you, sir.
The doctor. Yeah. Okay. So in the next level, I am not changing this 0th position, but 2 I will swap with this or this. So that will make 2 instances, 1, 2, 3 as it is. Otherwise 1, 3, 2. And then I becomes 2, that is n minus 1. So this is, I am not going to change this, 1, 2, and here 1, 3. And I am concentrated on permuting everything after starting at index 2, but this is just one element, so I will just print 1, 2, 3. Here I will print 1, 3, 2. Okay. Here also I will do a similar thing, 2, 1, 3, 2, 3, 1. Print this. Here 3, 2, 1, and 3, 1, 2. So they will be printed in the sequence 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, and 3, 1, 2. Let us see that this thing happens. 3. First 1, 2, 3. Then 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, 3, 1, 2. Okay. So maybe you write the recursion tree for n equal to 4, just one more level. So add 4, 4, 4, 4 everywhere, and then see that this works. Anyway, I understand that this program is not so easy. A lot of things you need to understand how recursion really works. So in the next class, I will give you another example. This is the Tower of Hanoi problem. Anyway, this is yet another very interesting example of recursion. But there are several other points. Yeah, if anybody has a question, please.
So which one problem, sir?
Yes.
So which problem you are talking in next class, sir?
Oh, well, that is called Tower of Hanoi. I will tell it. When time comes, I will tell it, but let me understand that this essential idea is clear. A function making recursive call of itself and achieving certain task by, in some sense, reducing the size of the argument.
Sir, if a function calls another function and within that function the other function is called, like two functions call each other, will that also be an example of recursion?
Okay, that's a good question. So suppose f calls g, g again calls f. So of course we can call these things recursive, or you may call this mutually recursive. Yes, these are also instances, and you have, it is also possible that f1 calls f2, f2 calls f3, f3 calls f4, and maybe f4 again calls f1. Okay, So these are all actually examples of mutually recursive functions. We can call them recursive. Yeah, no problem.
Okay, sir.
Okay, then maybe I will just okay, so maybe I just take 5 minutes to.
Sir, please can you show the code part again?
I will post it. You can download. After the class, I will post it.
Sure.
Okay, or maybe instead of starting a new topic, I just add one thing. Let me do one thing. Okay, so what I will do, I will also print how many lines are printed. Okay, so for that, I will use a sum variable s. Okay, now when I am at this case, I have just printed one line, so I will just return one. Okay. Otherwise, in general, I am making recursive calls and initialize the sum to 0. And I will simply add this. Whatever the ith or jth recursive call makes. And then I will return s. Okay. And here I stored this value. Okay. And I will just print these many permutations. L. And let us see how it works. 3, 6 permutations. 4, 24 permutations. 10, 360, 2880, right? Let us wait. 360, okay. Something like that. I do not fully remember. So 362880 permutations. Okay. So this additionally illustrates how you can play with return values. Is this logic clear? How many lines are printed? As many permutations are there. So here I am printing one line and therefore I am just returning one. But here actually I am not printing anything, but I should add up how many lines are printed by each recursive call. Therefore I use this s, the sum variable s, as an accumulator. And whenever I get some number of lines printed from this call, I will add them up. And eventually I will return that sum. Is that clear or not?
Sir, in permute you have written an0. L equal to permute.
A, N, 0. A is the array.
So y0, it should be I think.
No. Initially I is 0. Look at this. Yeah, here I is 0. Okay, so whatever this I is, I am starting replacing things with the 0th position, 0th index. Okay, then I will call on I equal to 1, then on I equal to 3, then on I equal to 4. Okay, so the initial value of I that I make in the call is I equal to 0. Okay, this will make a call on I equal to 1. Those things in turn will make a call on I equal to 2 and so on. Okay or not?
Sir,
Yeah.
I did not understand how you calculated total number of permutations because S is a local variable, so
Variable, local
unable
variables.
to visualize.
Yeah, you cannot visualize. Okay, let's see. Let's once again look at this example, how it works. Okay. So S is a local variable, but I am returning this and storing it somewhere. Okay. So after a function returns, this local variables are no longer existent. You cannot call them. But whatever this function is returning, that thing, if you store somewhere, you can use it. That value. Not perhaps with the name S, but within some other name. Let us see how it happens. So I am returning 1 when I am printing a line. Otherwise, I am simply adding up the values returned by the child, I would say, recursive calls. So here I am printing one thing. So I am going to return 1. Okay. And here also I am returning 1. And the local variable S of this invocation stores in this S the combined contribution of the different return values, right? So S is initialized to 0, and whatever this function returns, I add that value to the accumulator S, and eventually I will return S. So in the first call, it gets a value 1, so S becomes 1. The second call returns another 1, so S now becomes 2, and then there is this loop breaks, so that S value here now stores 2, right, this variable. This then returns this 2 to the next level. And the similar thing happens here. 1 is returned, 1 is returned, 1 is returned, 1 is returned. So this invocation, okay, initializes. Now this is the S of this. It has nothing to do with the S of this or S of this or S of this, right? This initializes S to 0. After this call, first recursive call returns 2. It updates that S to S plus 2, that is 2. This returns 2. Then this function updates the value of S to 2 plus 2, 4. Then this returns another 2. So the S value here now becomes 4 plus 2, that is 6. So that is now 6. The sum is returned to main. Okay. Is it clear now?
Yes, sir.
Okay, good. Yeah. Tell if there is any other question.
Sir, what will be the complexity of a recursive this thing?
Let us not be about this for the moment. I suggest that let us leave this topic now. There is a mathematical way of tackling the running time of recursive functions, but let us not worry about this. It's sufficient for the moment that you understand how recursive calls are made.
So, suppose we declare a variable inside a recursive function, then this recursive function, every time it calls itself, this variable will again be declared and more memory will be taken. So by the time the entire recursion is done, we actually like if we go to the top level of the recursion, we have declared a lot of memory space. But in case of iteration, it works only with a few variables declared and not much memory allocated to that. So why do we use recursion in spite of that, like instead of iteration?
Try to, I would say, that is the reason I have given you this example. try to write an iterative program doing this same thing on a general value of n. Then you will understand how recursion simplifies your life. And actually, this is not too much, I would say, space inefficient, because you are using this array A in every iteration. Of course, you have 3 variables here. That is private. Okay. But you just try to do it iteratively. Okay, this code.
Okay, sir.
Okay. And then you will
Yes,
really
sir.
understand
Because
how
arrays are like only the memory location is accessed, no new declaration is done. So that is why this one is efficient.
no, this is these things are these local variables are this array is shared, but this J, T, and S are I would say uh, private to each invocation. So this memory is wasted in a sense, but you just try to do it iteratively, and then you will understand. It's very difficult to do it iteratively.
Okay, sir. Got it. Thank you.
Yeah, tell if you have any other doubts. So I will take another hour for completing the remaining issues of recursion, and for another example, the tower of Hanna example. Today I am done. So
where will you upload this code
this code.
for permutation?
Yeah, this code I will upload. Why not?
Sir, I didn't understand the code part, sir. So why you use t is equal to ai is equal to aj?
So this is just a swap function. Okay, I will just write a code of this. I will just not write a code. Just as a this is swap AI with aj, and I am doing exactly the same thing, but it's essentially a swap back. Okay, and here I would say make recursive call. Of course, it is obvious, but you can see. Okay, so that was our original plan, right? I will swap Ci with Ci or Ci plus 1 or Ci plus 2 or Cn minus 1. That is precisely what this is doing. J equal to I to n minus 1. It is swapping, making the recursive call for doing the recursive part or the remaining part, and then once again swap back so that the array is in the original shape. Okay. Okay, I will upload this. So look at it and try to understand how recursion works. Okay, it's not necessarily so simple as the Fibonacci recursion or factorial recursion. It's much more complicated than this. Okay, so tell me if you have any other doubts. Let me clarify, otherwise let us stop.
Thank you, sir.
Sir, one more question, sir. Is array sorting in the syllabus? Like, is it in the syllabus of array?
Please repeat.
Array sorting, like using an algorithm, is it there in the syllabus?
Array sorting. Well,
Yes.
we actually have not covered sorting algorithms. If it is in the syllabus, we will explicitly mention this is the sorting algorithm, you write it.
So for tomorrow's test, we are asking.
Yeah, I am telling you for tomorrow's test only.
Oh, okay.
If we want to give you write a sorting algorithm, of course we will not say that you implement XYZ sort. We will specifically mention XYZ sort works this way. So now you write your code. This is not an algorithm design course. We will tell you the algorithm precisely. Unless
So we just have to do the implementation, if at all.
Unless of course obvious from your higher secondary knowledge.
Yeah. Okay.
Those things we will not say. But if there are any new algorithms, we will mention specifically.
Okay, sir.
Okay.
Thank you, sir.
Thank you, sir.
Then
Thank you,
don't
sir.
forget to log in tomorrow a little earlier, 10 minutes earlier in module, Institute module. Okay. Okay, so best of luck for tomorrow's test and take care. Okay.